Okay, on to question 2. Part A. Write q minus root 2 over 1 minus root 2 in the form of a plus bq, leaving surds in your answer. Okay, so this one you need to rationalize the denominator, so you need to multiply by the conjugate. So 1 plus root 2, or 1 plus root 2. So then you're left with q minus root 2 times 1 plus root 2 over, well, it's a difference of 2 squares, and you get a squared minus b squared, so it's going to be 1 minus 2, which gives you negative 1. And so when you have negative 1 resulting at the bottom here, you can then transfer that negative 1 to the numerator. And when you have a negative, you can then reverse the sign of one of these brackets here. So let's choose the first one. So this turns into root 2 minus q times 1 plus root 2. And then you expand this out, you get root 2 plus 2, and then minus q, and then minus root 2q. And then to factorize it in the form that they want, a is going to be 2 plus root 2, and then b is going to be negative 1 minus root 2 times q. And that is the answer. Okay. Part B is going to be find the values of p so that the quadratic equation px squared minus px plus c equals 0 has real and distinct roots. So real meaning the discriminant is greater than 0, and then distinct meaning meaning that there are 2 roots, and so it's greater than 0. So we want b squared minus 4ac being greater than 0, b being the negative p, and then squared, minus 4 times a, which is p, and then c, which is 6, greater than 0. So you get p squared minus 24 p greater than 0. Can factorize out p here. You get p minus 24 is greater than 0. So your solutions to this quadratic is p equals 0 and p equals 24. So then what does this look like graphically? Well, it looks like this, from 0 to 24. And we're interested in when this function is greater than 0, or positive. So you're looking above the x-axis. So it's going to be here and here. And so it is when p is less than 0, or when p is greater than 24. So p is greater than 24, or p is less than 0. So that's your answer there. Okay. Next question, part C. 3 minus I is the root of the equation z squared. Okay, so z equals 3 minus I as a solution. And so for the conjugate root theorem, z must also equal 3 plus I. And we have the equation z squared minus a plus bi times z plus 4 times 1 plus 3i equals 0, where a and b are real. So you need to find the values of a and b and the other root of the equation. Well, we've already found the other root of the equation. We just need to solve for a and b here. So here we just need to substitute in z into this equation. So let's use this one, z equals 3 plus I. So you have here z squared, which is 3 plus I squared, minus a plus bi times 3 plus I plus, well, we can expand this out into 4 plus 12i immediately. And so then expanding all these brackets out, you get 9 plus 6i plus I squared minus 3a plus ai plus 3bi plus bi squared plus 4 plus 12i equals 0. You can see here that this I squared becomes minus 1. So you got 9. So the real parts are 9 minus 1. 9 minus 1. So let's just group all the real parts. 9 minus 1 minus 3a. And then this I squared again turns into negative 1. So it's minus b, and then plus 4. And then the imaginary parts are going to be the 6i, and then minus a, minus 3b, and then plus 12. This equals to 0. So simplifying this down, you get 12 minus 3a minus b plus I times 18 minus a minus 3b equals 0. And you can see that the real part and the imaginary part both need to equal 0 in order to make this equation true. So 12 minus 3a minus b equals 0. Or in other words, 12 equals 3a plus b. And then 18 minus a minus 3b equals 0. Or 18 equals a plus 3b. So then let's just solve this equation using our calculator. So go into equations, two unknowns, your coefficients are 3, 1, 12, 1, 3, and then 18. And you get here that a is equal to 2.25 and b is equal to 5.25. I hope that's right. Okay, on to the next part, part D. So find the exact solutions for this equation. Z to the power 4 minus z cubed equals 1 minus z. So, and then graph the roots. I don't want to graph them, I don't care enough. But you can see here that this left-hand side you can factorize as z cubed times z minus 1. And you can bring the 1 minus z to the other side to give you plus z minus 1 equals 0. Notice how if you put brackets around that, you can factorize out z minus 1 here as well. So you can factorize out z minus 1 from z cubed plus 1 equals 0. So now you got two solutions, or two parts here. Z equals 1 or z cubed equals negative 1. Now this is a quartic, so there needs to be 4 different solutions. If you just cube root this, you'll just get an answer of negative 1. But obviously it's a complex numbers paper, so you should change this into a polar form. And you can kind of imagine that on the Argand diagram, that where negative 1 exists is just over here. And so the absolute length, or the modulus here, is just 1. And then the argument over here is going to be half a rotation of the circle, which is pi. So that's the argument. So then this is just simply cis pi with a modulus of 1, but we don't write the 1 there. And then we can cube root both sides. So you have cis of pi over 3, and then our general solution tells us that there's plus 2 pi n over 3 as well, which we can join together as simply just cis of pi plus 2 pi n over 3. So then when n equals 0, z is equal to cis of pi over 3. When n equals 1, z equals cis of 3 pi over 3, or just cis of pi. And then when n equals 2, z is equal to cis of 5 pi over 3. And then again, there's only 3 solutions because the power is only 3. So we can stop there. And then those are our answers. And I don't want to graph them because I don't care. Okay, and then part E. Find the solutions for z to the power of 2 over 3 minus 1 plus I equals 0. So here we also want to form it into a de Moivre's theorem, or like a polar form. So z to the power of 2 over 3 is equal to 1 plus I, which we can convert into, so we can imagine that on the Argand diagram again. This is at 1, and then this is at I, so over here. So the length of that is going to be, well, it's got a height of 1 and a horizontal distance of 1, so it's just going to be square root of 1 squared plus 1 squared, which is a square root of 2. And the modulus, the argument here, well, that's going to be just pi over 4. You can double check that if you want. There's just 1 over 1. But it should be pi over 4. Because the real part equals the imaginary part. Okay, so we can change this into root 2 of cis pi over 4. You can rewrite this as cube root of z squared. So we can cube both sides first. So we have z squared is equal to root 2 cis of pi over 4 to the power of 3. And then, well, actually, yeah, so you can cube it first. And what you then have is root 2 cubed, which is just 2 root 2 cis of 3 pi over 4. And then after that, you can square root both sides. So you have the square root of 2 root 2, cis of 3 pi over 8. And then there are two solutions, so you have to add on 2 pi n over 2. And you can see that the 2's will cancel each other out, so let's just plus pi n. So if you let n equal 0, then z is equal to root 2 cis of 3 pi over 8. And then if n equals 1, then z is equal to root 2 of cis, well, you're adding on pi, so that's going to give you 11 pi over 8. And so there's just two solutions there. That should be the answer.